Hey guys, I'm Pat Kelly. Okay, the challenge in this problem is they give us a sequence and they want us to find a formula for the nth sum and then to prove the validity of that formula. Okay, so let's get started. Realize that what they're asking for is that S sub n, the partial sum. We have to come up with a formula for that. What I'd suggest is you lay out the first several partial sums, and then try to find a pattern. Okay, so if you remember with our partial sums, to start, S sub 1 is actually just the first term. Okay, S sub 2 equals the sum of the first two terms. And of course, I do want to say that yes, that equals 6 because we're going to end up looking for a pattern in these results. So if I continue, let's do a couple more. With S sub 3, I'm going to try to remind you that it's actually the previous partial sum plus the next term, so 9 in this case. And do that arithmetic, and you get 15 in this case. I might end up using this later, so this reminds you that this 6 came from here. Partial sum of the next guy is the previous guy plus the next term. Okay, let's try that again. S sub 4 equals the 15 that we just calculated plus the next term in the sequence, which is 13, and that equals 28. Okay, that equals 28. So what? All right, I can't sugarcoat it. This is a tough part of the problem. What you're going to do next is look at these partial sums that you just calculated, 1, 6, 15, 28, and try to find a pattern, okay? You'll end up thinking about this for a while with some of these problems. Maybe even like overnight, you'll sleep on it. But what you need to do is come up with a guess at what S sub n looks like as a formula. And I'm even using the word guess here because I definitely want to convey to you that this is not something that should just immediately come to mind necessarily for some of these problems. Like, yeah, you're supposed to know that. No, it's a guess. It's a conjecture. You're going to see if you're right. So you make your best guess, and then the cool part is you prove that you're right. Then it's no longer a guess. So I had to think about this one for a little bit, and I came up with 2n squared minus n. Please again realize that should not necessarily come to you immediately. But that's my guess. Let's see if we're right. To see if we're right, we're going to try to prove that it's correct, that it's accurate. Let's prove that we're right. And the tool I'm going to use is mathematical induction. So let's get into our mathematical induction steps. Remember, there's step 1, step 2. And step 1 is to always show that the statement is true for n equals 1, or n equals the lowest value that you're looking for the statement. Okay, so to show it's true for n equals 1, we're going to look at this guess of ours and put a 1 in for n and see if that equals 2. Put a 1 in for n squared minus 1. See, of course, just putting a 1 in for n there. But it's actually even still a question mark. I'm trying to show that that's true. Now let's do some arithmetic. 2 times 1 is 2, take away 1 is 1. And I've actually just answered the question mark. I'm going to check mark it. We're confirming it because S sub 1 we actually already knew equaled 1. Okay, so that did work. Great. Onward with mathematical induction, step 2. Step 2 is always an assumption. The first part of mathematical induction, step 2, is to assume that the thing you're trying to prove is actually true for the kth case. So put a k in for n everywhere. And this equal sign does not get a question mark over it. We're assuming that it is true. K in for n, let's assume that's true. And then the challenge in step 2 is you've got to get what you want, And what you want is for this statement to be true for the k plus 1th case, right? So we want this expression to be true, but with a k plus 1 in everywhere for n. So we want this to equal, I'm looking at this and putting a k plus 1 in, wherever there was an n, k plus 1 squared minus k plus 1. And let me add in yellow here, I don't know that this is true, this equal sign. This is what we want to be true. So let's see if we can get there. Now, I'm actually going to do ourselves a little bit of a favor now. It'll pay dividends later, very soon later. But the favor I'm going to do for us is to clean this right side up a little bit. Okay, I do some algebra. The playing around that you almost always do with this type of problem is algebra. Almost always comes down to algebra. So algebraically, what I'm seeing here is, let's factor out k plus 1. So k plus 1, since it's a factor in each of the two terms, let's factor it out. Let's see what's left over. The 2, one of these k plus 1s minus, and then this k plus 1's gone, but don't lose the 1 that would be there after you do your factoring out, okay? And this equals, if you don't mind me squeezing it in over here, the k plus 1 still, and I'll just clean up the square braces. 2k is my only k term. And the constants will be 2 take away 1, so that looks like plus 1. And I'm done. The favor that I'm doing for us is we want this s sub k plus 1 to be true. And I think we're going to see this version of it after we do a little bit of work. So this is still in the category of what do we want. That's what I want. Okay? All right, now let's get to it. In order to get there, I got to start with s sub k plus 1 again. Let's look at s sub k plus 1. But, and this is important, you don't start with this by grabbing what we want it to equal. That's cheating, that's getting to the end of it. What we got to do is start with what you know s sub k equals. What does it mean to begin with? What it means is s sub k, the previous partial sum, plus the next term in a sequence, which we usually denote with that lowercase a, in this case, sub k plus 1, okay? If I can remind you, we actually even did that earlier. We did that thought process of, hey, your next partial sum is the previous partial sum plus the next term, okay? That's exactly what I'm doing here. All right, now, what that suggests to me here is I do need an a sub k plus 1. I need to know what the k plus 1th term is of this original sequence. So let's go over here and do just a little bit of work. Some work that you've done before is, given a sequence, can you come up with the nth term of that sequence? Remember this type of problem? You've got to come up with a sub n, given this sequence. That can be a problem in and of itself. What I can do with mine is actually recognize that this is arithmetic. Up by 4, up by 4, up by 4. So the nth term here will be 4n minus 3. That might take a little bit of work to get, but that works here. That's correct. So let me come back over here and continue my work with s sub k plus 1. This equals, and I'm gearing myself up to replace this a sub k plus 1 with what we just figured out. But before I even get there, see this s sub k? This s sub k, I'm going to replace from here this s sub k, because we're assuming that s sub k equals all of this. Okay? So here, I will write the right-hand side of that 2k squared minus k. And again, that comes from my squiggly orange equation there, okay, the assumption. All right, then continuing plus, and now I'm going to use my expression, my version for a sub n over here, but put a k plus 1 in for n, 4 times k plus 1, and then it was minus 3. Okay, and now some algebra. All right, clean up a little bit. So this equals 2k squared minus k plus 4k plus 4 minus 3, that looks like plus 1. I should have done a little bit more in my head because minus k plus 4k, that's just 3k. So 2k squared plus 3k, and then plus 1. So what? Well, factor that. Good old trinomial quadratic. Does it factor nicely? A little bit of a spoiler alert. Yes, it does. 2k and k. The constant term of 1 is going to be 1 and 1. Everything's positive. That looks good. And I'll actually even argue that looks better than good. It looks great because that's what we wanted. We wanted this to equal that. It does, which means we've shown that the s sub k plus 1th case also works when the s sub k case works. In other words, you've proven it. You're done. Pat yourself on the back. Go try some other problems.